Hello everyone, my name is Vijay Kumar and I am here to discuss about microprocessors. Microprocessors, the brain of modern technology. Welcome to the world of microprocessors. These tiny electronic chips are the foundation of all modern technology. From smartphones to self-driving cars, let's explore the fascinating world of microprocessors and their impact on our daily lives. Here we will discuss about the major milestones in the development of the microprocessors. The first microprocessor was developed in 1971, which was known as the Intel 4004, which contained 2300 transistors and could perform up to 60,000 operations per second. And the next breakthrough processor was Pentium 4, which disrupted the market and was a game changer, which had 42 million transistors and could perform up to 1.5 billion operations per second. Well, it was a game changer. Now moving on to the latest microprocessor like Apple A12 Bionic, which contains nearly 7 billion transistors and can perform over 5 trillion operations per second. Well, interestingly, it is 80,000 times more faster than the Intel 4004 microprocessor, which was the first microprocessor. Key components. The microprocessor's major component are CPU, memory and input-output devices. CPU. The CPU or central processing unit is the brain of the microprocessor. It performs all the calculations and instructions that make our devices work. Memory. Memory stores data and instruction for the CPU to access. There are different types of memory including ROM and RAM. Input-output devices. Input-output devices like keyboard, mouse and monitor allow us to interact with our devices and see the results of our instructions. Today, microprocessors have very vast applications like from smartphones to healthcare to self-driving cars. Like in smartphones, microprocessors power our smartphones, allowing us to stay connected, take great pictures and play games on the go. You must have heard about Snapdragon and MediaTek microprocessors. Like in self-driving cars rely on microprocessors to interpret data from sensors and make decisions in real time. You must have heard about Elon Musk Tesla. Healthcare. Innovative medical devices like pacemakers and insulin pumps are powered by microprocessors, making life easier for millions of patients worldwide. Let's compare the microprocessor with the other computer components, CPU versus GPU. CPUs and GPU both process data, but CPU are better suited for sequential tasks while GPUs are optimized for parallel processing. CPU versus RAM. CPU perform calculations while RAM store data temporarily. The more RAM a computer has, the more application can handle simultaneously. CPU versus hard drive. CPU perform calculation while hard drive store data permanently. The speed of a hard drive can also have a big impact on computer's performance. Let's talk about current and future trends related to microprocessors. Artificial intelligence. AI is one of the hottest trends in technology and microprocessors are the heart of this field. Advances in neural networking and machine learning are driving the development of powerful new microprocessors. Internet of Things (IoT). The IoT is a rapidly growing field that depends on microprocessor for real-time data processing and communications. As far more devices becoming connected, the demand for powerful, energy-efficient microprocessor will continue to grow. Quantum computing. The future of computing may lie in quantum computing. The future of computing may lie in quantum processors, which use quantum mechanics to perform calculation far beyond the capacity of classic computers. Companies like IBM and Google are developing powerful new microprocessors to drive this technology forward. Discover the world of microprocessors. Explore the power of assembly language programming and the low level control it provides over hardware. Learn about registers, instructions, and addressing modes. Discover how assembly language programming can be used in embedded systems device drivers, and operating systems. Assembly language programming. Low-level programming language. Assembly language is a low-level programming language that provides direct control over hardware. It facilitates efficient processor and memory utilization, making it useful for optimization and debugging purposes. Instructions. Assembly language includes a set of common instructions such as MOV, ADD, SUB, and JMP that are used to manipulate data. This instruction offer a high level of control over hardware but required a good understanding of a underlying architecture. Embedded systems. Assembly language is often used to create programs that run on an embedded system. This program control hardware devices such as sensor and actuators. They are the integral part of the system. The power of registers. What are registers? Registers are small, high-speed, on-chip storage areas that are used to hold temporary data and memory addresses. They play a critical role in the execution of assembly language programs. The importance of registers. Registers are crucial in providing high-speed access to memory locations and speeding up execution time. They aid in optimizing code and help perform arithmetic and logical operations on data. Exploring register types. There are several types of registers, including data registers, address registers, and control registers. Each type serves a specific purpose in executing code and performing operations. Mastering addressing modes in microprocessors. Immediate addressing. Immediate addressing mode allows data to be directly specified in the instruction itself. This mode is helpful when using constant in arithmetic or manipulating data. Direct addressing. Direct addressing mode specifies the memory location of the data. This mode is useful when accessing variables stored in specific location. Indirect addressing. Indirect addressing mode uses a memory reference to access the target memory address. The mode is helpful when accessing array or structures. Indexed addressing. Index addressing uses a big register and an offset to calculate the memory address of the data. This mode is useful in array operations and when accessing multiple instances of the same data. Application of assembly language programming. Embedded systems. Assembly language is a critical programming language for controlling and automating industrial processes. It is used in robotics, auto manufacturing, and other fields that rely on automated systems. Device drivers. Device drivers are software programs that help hardware devices communicate with the computer's operating system. To interact with the hardware directly, low-level language like assembly are necessary for efficient programming. Operating systems. Assembly language programming is essential for writing low-level routines in operating systems. It helps the tasks such as interacting with hardware devices and scheduling processes. Pros and cons of assembly language programming. Advantages. Assembly language provide a high level of control over hardware, optimizes code efficiency, and offer a possibility for program optimization and debugging. Disadvantages. Assembly language programming has a steep learning curve, longer development time, and a less portable and maintainable code compared to other high-level programming languages. Uses of assembly language. Assembly language programming provides low-level control over hardware, enabling efficient utilization of memory and processors. It is useful in embedded systems, device drivers, and operating systems. While assembly language may not be the easiest language to learn, its benefit can be game-changing in terms of program efficiency and optimization. The magic of assembly language. Assembly language is a low-level programming language that offers developers precise control over the microprocessor's hardware. It is an essential knowledge for any embedded system engineer. The benefits of assembly language. Speed. Assembly language is faster than high-level languages such as Python and Java. This allows for real-time instruction. Size. The small size of the language makes assembly programs more efficient in terms of memory usage, making them ideal for embedded systems with limited resources. Control. The low level of programming, together with the direct control of the hardware, enables precise optimization for a specific microprocessors. Registers and memory. Registers. Registers are a small location inside the microprocessor used for quick data access. Assembly language programmers must learn how to efficiently use them. Memory. Memory holds data and instruction in a microprocessor. Assembly language programmers must know the available memory and how to use it efficiently. Cache memory. Cache is a high-speed memory that stores frequently used data to speed up access. Assembly language programmers must learn and understand how cache works to optimize their code. Instruction set of a microprocessor. There are three types of instruction set of a microprocessor: data movement, arithmetic operation, and logic operations. Data movement. Data movement stores and load data between memory and registers and registers. Arithmetic operations: addition, subtraction, multiplication, and division of data in registers. Whereas logic operations, bitwise and logical AND or XOR operations are data in registers. Data transfer and manipulation operations, MOV, copies data from one location to another, one of the most fundamental instruction in assembly language. There are various MOV variation in different types of data, INC/DEC. Adds or subtract from a register or memory location, commonly used to loop through an array to increment, decrement a counter variable. Add sub, perform addition or subtraction of two registers or memory location. MULDIV, multiplies or divides the two registers or memory location used to complex mathematical operations. MULDIV, multiplies or divides two registers or memory location used for complex mathematical operations. Examples of assembly language programs in microprocessors. Their examples are Fibonacci sequence, LED blinking, sorting algorithms, and signal processing. In Fibonacci sequence, we generate the sequence using recursive subroutines, loops, and conditional jumps. In LED blinking, we turn off and on a LED with various delay, control the pulse with modulation of the light, and read input pins. Sorting algorithms. In sorting algorithms, we implement sorting algorithms such as bubble, quick and merge sort in assembly language for maximum efficiency. Signal processing, filtering, amplifying or demodulating signal from sensors, microphones or antenna in real time using assembly language. Conclusion and potential implications. Microprocessors have a long way since the early days of the Intel 4004. Today, they power everything from our smartphones to our cars to our medical devices. The future of microprocessors is bright, with exciting new trends like AI and quantum computing on the horizon. While microprocessors have brought us incredible advances in technology, they also raised important ethical questions about privacy, security, and automation. As we continue to rely more and more on microprocessors in our daily lives, we must carefully consider their potential implications in society as a whole. Thank you.